Now here's our running example once again. Now let's suppose that at time 0 I'm in state 2, and I want to know the state at time t equals 1. What's the distribution for the state at time t equals 1? Well, how do I get it? Well, I just look at this row. The second row of this transition matrix tells me the distribution for the state at time t equals 1. It's the one-step transition matrix. Now what's another way to get row 2? Well, I can take this vector, which has a 1 in entry 2 and zeros everywhere else, and I can multiply this row vector by this matrix. And then what do I get? I get row 2 of this matrix. So this is my distribution at time 0, and I multiply that by the transition matrix, and I get the distribution at time t equals 1. And in general, at time 0, I don't have to be in a fixed state. I can be in a distribution over the states. So let mu be an arbitrary distribution over the n states. So what exactly does that mean? That means mu is this vector, this row vector of size n, and it's a probability distribution, so the sum of these entries is exactly 1. And all these entries are between 0 and 1. Now we're replacing this vector by distribution, mu. Then here we have p, and then we get a distribution at time t equals 1. So let's call this mu 0 to denote the distribution at time 0. And over here, we get a distribution for the time t equals 1. So let's call this mu 1. And in general, if we take mu 0, so the distribution at time 0, and multiply it by this matrix P, the transition matrix, then we get the distribution for the state at time t equals 1. So we take this row vector for the distribution at time 0, multiply by one step. So we do one step of our random walk. And then we get the distribution, the row vector, for the state at time t equals 1. Now the key property is that for a stationary distribution pi, for any stationary distribution pi, so if I'm in this stationary distribution at time 0, or at any time t, and I look at the state at time t plus 1, then what is the distribution going to be? Well, once I reach this distribution, I stay in it. It's the limiting distribution. It's like a fixed point of the process. So once you reach a fixed point, you stay in a fixed point. And that's the same for a stationary distribution. So if I'm in the stationary distribution at time t, and I do one step, then I'm still in the stationary distribution pi. So pi times p equals pi. What does that mean in terms of linear algebra? Well, this pi is an eigenvector with eigenvalue 1. So pi is an eigenvector for this matrix P. And it's an eigenvector with eigenvalue 1. 1 turns out to be the largest eigenvalue for this matrix. So this is the principal eigenvector for this matrix. Now there can be multiple eigenvectors with eigenvalue 1. We're going to look at situations where we know that there's at most one eigenvector with eigenvalue 1. So there's at most one stationary distribution.